All right, so then the next section discusses the intermolecular forces, or van der Waals forces. Again, these are between molecules, not within a molecule. There are some examples within a molecule, but primarily here we're focusing on between molecules. So if one molecule is nonpolar, another molecule is nonpolar, and they don't have any partial charges, you might say, well, why would they attract? If they get close together, they don't have any partial charges. But we know that the electron clouds are fluid, and they can move around. And this has a big impact on the types of properties substances undergo. When I have a gas versus a liquid and a solid, the organization of the particles is primarily governed by how polar they are and whether or not they can form these intermolecular attractions. Substances that are usually low in polarity and don't form strong intermolecular attractions are often gases at room temperature, because if I've got my molecules moving around at room temperature, they have a little motion on average. If they come close together and they're nonpolar and they can't form any really strong attractions because they don't have any permanent partial charges to line up, when they come together, they'll just bounce off one another. They won't stick. And that's the way gases behave. We'll talk more in detail about later chapters about gases, solids, and liquids. But in liquids and solids, the particles are close together. Why are they close together? Why are liquids and solids so much more densely packed with matter than gases? Why are the molecules close together? It's because of the intermolecular attraction. And lots of different properties for liquids and solids, like melting point, boiling point, viscosity, density, surface tension, all these different properties we'll talk about later, are affected by the intermolecular attraction. So understanding and recognizing and labeling the intermolecular attractions now is really important in later sections when we start to talk about the impact of those intermolecular attractions and how it affects the properties of substances. So, dipole-dipole interactions, the most straightforward one. So we now know if we have a polar molecule, or a molecule that has a dipole, it can line up next to another polar molecule that also has a dipole, and their opposite charges can line up and they can form attraction. So this is meant to show that the red are the areas of partial negative, the blue are the areas of partial positive. If I've got a lot of molecules in a sample and it's a liquid, they'll be close enough together, and usually they'll be a liquid because one molecule is negative will get next to another molecule positive, and they'll form an attraction. And so this is kind of organized in that way, where you see all the reds are next to blues, all the blues are next to reds, and those small partial charges between all the molecules kind of form a network of attractions, and that's what pulls the liquid together. If I want to evaporate a liquid, what I have to do is get each one of these individual molecules to separate from the others. So the more polar they are, the stronger they're attracted to one another, the higher the temperature is going to be required to boil that liquid. In a solid, though, if it's held together through dipole-dipole attractions, usually it's also organized. So in the solid, I can form a greater number of attractions, because in the solid they're lined up in a more efficient way, so that all the negatives are next to positives and all the positives are next to negatives. That allows the molecules to form the greatest number of intermolecular attractions. And so if I take a liquid and I decrease the temperature and slow it down, then sometimes these things will line up because their attractions will be pulling them together and organizing them in a way that allows them to make more attractions as the attractions force them to organize. So how strong will dipole-dipole forces be? It depends on the magnitude of the partial charges involved in the dipole. The greater the electronegativity difference between the atoms, the more partial charge I have, the better that molecule will be able to attract another molecule with partial charges. And that can be illustrated here. So if we look at these molecules, maybe we can draw these blue structures out. But propane has virtually no dipole. It's pretty much symmetrical. It doesn't have one side negative, one side with a partial positive. So in terms of its properties, it has a very low boiling point. Molecules of propane aren't really polar. So they don't attract other molecules of propane well. It doesn't take much energy. Even at negative 42 Celsius, there's enough motion for those molecules to separate and become a gas. On the other end of the spectrum, you have acetonitrile. If you draw the Lewis structure for that and look at its polarity, you can see that it's a pretty polar molecule. There's a triple bond here. So there's a decent difference in electronegativity between carbon and nitrogen. So I have some of these areas. All my arrows on average are pointing to the right here. Right? There's most of the partial negative is going to be on the right-hand side of the molecule, and most of the partial positive is on the other side. The central position of negative is on the right, central position of positive is on the left. So I have an arrow here. So if that molecule gets next to another molecule of the same type, then the positive end of one molecule will attract the negative end of the other. If I want to evaporate that, I have to break the molecules away from one another. Right? So when I evaporate or boil the compound, I'm not breaking the covalent bonds up. Common misconception. I'm not breaking up the molecules. I'm separating one molecule from a neighboring molecule. And the ability to do that depends on how strong the intermolecular attractions are. So dipole-dipole, you want to recognize is one of the intermolecular attractions. Another kind of subset of dipole-dipoles are hydrogen bonds. And as we said, hydrogen bonds involve especially strong dipole-dipoles or especially large quantities of partial positive and partial negative. So when a fluorine and a hydrogen bond, it's a big difference in electronegativity. It's one of the most polar covalent bonds. So that's going to create huge quantities of partial negative and partial positive. And so when another molecule gets nearby and does the same thing, this partial positive, partial negative attraction is known as a hydrogen bond. Hydrogen bonds are not covalent bonds. The hydrogen bond part of this is not here. The covalent bond between the hydrogen and the fluorine is not a hydrogen bond. Covalent bond is electrons that are shared that need to stay around both atoms to complete both their noble gas configurations. The covalent bond shifting toward the more electronegative atom creates partial carbons. The hydrogen bond is the attraction between the partial carbons. It's a dipole-dipole. It's an attraction between two different molecules and their opposite charges line up. It's just a special kind of dipole-dipole because when the hydrogen is specifically bonded to one of these three most electronegative elements, it will have its electrons pulled away from it dramatically, causing it to carry a very large quantity of partial positive. So when I have a highly electronegative atom sharing electrons with the hydrogen, that creates a large partial positive. When I have another molecule with a highly electronegative atom pulling electrons toward it, that creates a large partial negative. And then those can attract. And that attraction, usually shown with a dotted line, is known as a hydrogen bond. Another way to think about it is you need to make a hydrogen sandwich. To make a hydrogen bond, the hydrogen has to be sandwiched between two electronegative atoms. If on one side the element here is not a nitrogen, oxygen, or fluorine, or if on the other side it's not a nitrogen, oxygen, or fluorine, it's not going to be a hydrogen bond. It'll still be maybe a dipole-dipole, but it won't be strong enough to fit the threshold of being considered a hydrogen bond because it won't have large partial charges if there isn't a very electronegative atom involved in that. 7.32 asks us to look at ammonia. So let's take a quick look at that one. Ammonia is a nitrogen with 3 hydrogens. Ammonia is capable of hydrogen bonding. Ammonia is capable of forming up to 4 hydrogen bonds. A hydrogen bond is really an attraction between an area of partial negative. Oops. And this nitrogen will be partially negative because of the electronegativity difference there being quite large. It's that attraction between that on one molecule and the partial positive of another molecule. That is my hydrogen bond. In hydrogen bonding, there are so-called hydrogen bonding donor sites and hydrogen bonding acceptor sites. That is thought of from the perspective of the lone pair. It's another requirement to make a hydrogen bond. So we got our hydrogen sandwich here. The hydrogen is sandwiched between 2 highly electronegative atoms. It's sharing electrons with one through a covalent bond. It's forming a hydrogen bond or a strong dipole-dipole with the other. What's required for that, though, is not just these large partial charges, it's also required that the highly electronegative atom have a lone pair. Because that lone pair is really the center of negative charge for it. That's a pair of electrons on a highly electronegative atom. That's where the majority of the negative charge on that atom is located. And so it will be this lone pair that the proton or the hydrogen partial positive is attracted to. That's why we always draw our dotted line from the lone pair. Okay? And that lone pair is considered a hydrogen bond donor because it's kind of like it's donating or a little bit sharing its lone pair a little bit with that hydrogen because it's sharing some of its electron density where that lone pair is going to be shared with the hydrogen a little bit. So it's kind of a donor, and they call the hydrogen an acceptor. So each ammonia molecule could form up to 4 hydrogen bonds because it could line up with a lot of molecules around it to form one here, to form one here, and I can form one here. This one molecule in the center can form up to 4 hydrogen bonds. So anytime I've got a hydrogen that's forming a covalent bond, a shared pair of electrons with a highly electronegative atom, that hydrogen is capable of hydrogen bonding with another molecule. Anytime I have a lone pair on a highly electronegative atom, that lone pair is capable of forming a hydrogen bond with another molecule. And then the third type that they focus on in this chapter are dispersion forces or London forces, London dispersion forces. These involve temporary dipoles. Right? So here in this picture, what they're trying to show is the light blue ovals are meant to show non-polar molecules, molecules that don't normally have opposite charges on opposite ends. Right? Because the blue is positive and the red is negative. If there's no dark blue or red, then I don't have any charges. But what we recognize is that the electrons that are distributed around this molecule, right, there's atoms there, there's electrons around them, those electrons are fluid and they can shift temporarily. So if I have a sample of a nonpolar substance, at any given moment in time, some of the molecules involved might not have any partial charges. But as the electrons flow around, they will maybe create some partial charges in other molecules. Once like say this molecule creates a temporary partial charge, it will have a negative end and a positive end. Then if it's next to another molecule, the negative end will cause electrons to shift away and create a positive end, and that will create what's called London forces. So one molecule forms an instantaneous dipole that may induce the other molecule to become a dipole, and then they can form these temporary dipole-dipole type attractions that result from the temporary shifting of electrons. Questions about that? Okay, 7.23. Explain the term polarizability. Sounds like a made-up word. What is the relationship between polarizability and intermolecular forces? Polarizability is not a made-up word. I mean, it was originally, but it's a word that people use, and it's a word that exists now. Polarizability describes the ability of a nonpolar molecule to become polar. So it's basically exactly what it sounds like. If I have a molecule, and that molecule has very fluid electrons, then it's more polarizable. However, if the electrons around that molecule are held in tightly to the nucleus, and they can't shift around and be that fluid, it won't be as polarizable. So it's basically a way of describing the degree of fluidity for the electrons around an atom. And that is primarily determined by how far down the element is on the periodic table. Right? Because as we go from the top of the periodic table, every time we go down a row, we're adding more and more layers of electrons. And the outer electrons, when they're in layers 2, 3, 4, 5, 6, the further out they are, the more core layers there are, the more those outer valence electrons are shielded by the core electrons, the less tightly they're held to the nucleus, the more polarizable the atom will be. So if I have lots of these atoms with lots of layers of electrons moving around, those layers of electrons are very fluid, and they can easily shift to one side or the other and create a temporary partial charge and become involved in London forces. Small atoms, where their valence electrons are in energy levels 1 or 2, and they're not experiencing much shielding and they're quite close to the nucleus, those atoms are not very polarized because they hold their electrons much more tightly and they're not able to flow around and be fluid as much. So it's an important term that you want to make sure you understand what it means and understand. There are differences between different elements depending on how many electrons they have in terms of how easy it is for their electrons to flow around and create partial charges. What's the difference between a temporary dipole and a permanent dipole moment? A permanent dipole moment exists when you have opposite charges always on opposite ends of the molecule, because the molecule is asymmetrical and there's some electronegativity difference where one atom is pulling the electrons always to one side. A temporary dipole moment is formed on a molecule that would normally be nonpolar. So either there's no difference in electronegativity between the atoms, or it's a symmetrical molecule and I don't have opposite charges on opposite sides due to the symmetry. In a nonpolar molecule, I form a temporary dipole moment due to the instantaneous random shifting of the fluid electrons that happen to maybe go to one side or the other. Why is hydrogen bonding exhibited by some hydrogen-containing compounds and not others? Well, we're talking about hydrogen bonding. There are lots of compounds that contain hydrogen that cannot get involved in hydrogen bonding. Most of them involve hydrogen bonded to carbon. If I've got a hydrogen bonded to a carbon, maybe there's more than one carbon, whatever, these hydrogens cannot hydrogen bond. They have to be bonded or sharing electrons with a nitrogen, oxygen, or fluorine. Because if they're only sharing electrons with a carbon, then this bond isn't very polar. The electronegativity difference is pretty small. It's not a big difference. So the hydrogen only carries a tiny amount of partial positive. That's enough to maybe form a dipole-dipole, but it's not going to form a hydrogen bond, because a hydrogen bond is a strong intermolecular attraction that involves large quantities of partial charge, and that will only occur if the hydrogen has its electrons really strongly pulled away from it from the atom that it's sharing electrons with. And that will only happen if the atom is very electronegative. Yeah, maybe I'll skip the next one. It's not super relevant. So this illustrates the importance of London forces. So we think of, well, London forces are usually weak. Are they really that important? Is this fact that these atoms can temporarily shift their electrons around and create partial charges really that relevant? And it is, because it explains the property differences between fluorine, chlorine, bromine, and iodine, because these are all nonpolar, right? Two atoms of the same type, when they share electrons, the electrons should be spread out evenly. The only opportunity for it to form partial charges would be if they temporarily shift to one side. And as we were just saying, when we were talking about polarizability, fluorine is not very polarizable. It's one of the least polarizable atoms because the fluorine valence electrons are in the second energy level, and the fluorine's nucleus is holding them in. They can't shift around. They're not as fluid. But iodine, I should probably have drawn this with a much larger electron cloud in comparison, has more layers of electrons. Its valence electrons experience a lot of shielding. They're on the outside. They're able to be much more fluid and shift around. And so the iodine atom, at any given moment in time, maybe it won't be polar. But with so many electrons, what are the odds that they'll all be perfectly evenly distributed around the atom and not create any partial charges? So the electrons in the iodine shift around just by random chance. Most of the time, they're going to be creating some pretty large partial charges. And so when one iodine molecule gets next to another, those partial charges, they're temporary, but they're very significant because the electrons are shifting a lot. those partial charges can attract a lot. And so it's a solid at room temperature. The iodine molecules line up, make those attractions, and those attractions are enough to hold it together. In order to convert it to a gas, I have to impart a lot of energy and temperature and motion to break those London forces. The fluorine, on the other hand, though, forms very little partial charge due to the fact that the electrons are not nearly as fluid. And so when one molecule gets next to another molecule of fluorine, the amount of attraction they can make with one another is very, very minimal. So the point of this is to illustrate that even though we rank London forces as the least effective or weakest intermolecular attraction, if the London force involves large atoms with lots of layers of electrons, it actually could be much more significant than you would normally predict. It actually could be one of the stronger types of attraction, holding one molecule next to another molecule, having a big impact on its physical properties. This slide is meant to show the impact of hydrogen bonding. Right, so what do we see here? We see a trend. So let's ignore these 3 points at first. Just look at the rest of the points. We have this trend, right? Increasing from left to right. What is causing that trend? Well, let's look at the graph. We've got on the x-axis the period. On the y-axis, the boiling point. Right, so what we're saying here is, as I go from left to right, or as I go from period 1 to period 2 to period 3 to period 4, down the periodic table, the boiling point's going up. Right, so I can just take this first purple line. That's group 4A. That's carbon, silicon, germanium, tin. As I go from the top to the bottom, the boiling point goes up. So why is it that from carbon to silicon, as I go down, the boiling point goes up and up and up? What's the explanation for that?
The elements are getting stronger.
The elements are capable of forming stronger intermolecular attraction. It's not really the elements, it's the molecules, right? Because we're putting enough hydrogens on here to complete the noble gas configurations for all of them. So we're saying is CH4 is a very low boiling point. SiH4 is a higher boiling point. The difference is silicon versus carbon. And silicon has more layers of electrons, it's more polarizable, it creates better temporary partial charges to attract one molecule to the next, so more energy is required to separate those molecules and turn it into a gas. When I go to the next level down, I have even a more polarizable atom, more electrons to shift around and create temporary charges so the molecules can attract one another. So the intermolecular attractions, the London forces are stronger when I have more electrons. With stronger London forces, it takes a higher temperature to get those molecules to separate from one another and move around and become a gas. Because to go from a liquid to a gas, I have to break the intermolecular attraction. And so in all these rows, I have the same trend. The only exception is once I get to a molecule that's capable of hydrogen bonding, then that takes over as the primary force. And so if I'm thinking about the ammonia versus the pH3, the NH3 versus the pH3, what's the difference? Well, NH3 is here, the nitrogen is here, the phosphorus is here. The phosphorus is more polarizable. It has more electrons. So the pH3 intermolecular attractions between two molecules of pH3 should be pretty strong London forces because they've got this electron's ability to shift around and create temporary charges. It can form stronger London forces between two molecules of pH3 than it can form London forces between two molecules of NH3. So what's the difference? The NH3 is capable of the hydrogen bonding. Right? We just showed that a couple slides ago. Because the NH3, because the ammonia molecules have a very electronegative atom compared to hydrogen, that creates large partial charges to attract the molecules together. So hydrogen bonding is very important. If I try to imagine the same thing with phosphorus, the Lewis structure would look the same, except I'd have a phosphorus atom there. The difference, though, is that phosphorus's electronegativity is only 2.0. And hydrogen is, actually, I think it's 2.1. I think it's the same as hydrogen. So in the case of phosphorus, I don't really have any polarity here. I don't really have a dipole. So obviously, if there's no partial charges that are permanent on one end and on the other opposite end of the molecule, it's not going to be able to form these types of hydrogen bond intermolecular attraction. So it can only form London forces. it can form better London forces than the NH3, but it can't hydrogen bond. It doesn't have areas of permanent large partial positive and negative on opposite ends of the molecules to line up and form nice strong intermolecular attractions. So basically what we're saying here is, in general, the more electrons I put in a molecule, the stronger the intermolecular attractions will be because there's stronger London forces, and it will take more energy to separate those molecules and get them to become a gas. Except when the molecules have big differences in electronegativities that cause large permanent partial charges that create hydrogen bond attractions between the molecules, then it takes even more energy in general to cause the molecules to separate and become a gas. So let's label the types of intermolecular attractions these molecules can make. So I realize for the first one, A here, that this is symmetrical. Unfortunately, it's drawn as if it were flat, but it doesn't really matter too much here because even if I draw it in the correct geometry as a tetrahedral, I still know what a tetrahedral shape looks like, and I still know that that is completely symmetrical. So since there's no opposite charges on opposite ends of the molecule, London forces would be the only types of attractions between two molecules of CCl4. Looking at the next one, here I can see some big electronegativity differences. So actually what I should probably do first is to just go through all of these and label London forces. I'm trying to list all of the intermolecular attractions they could have. There's always the possibility of London forces, no matter what. As long as you've got electrons, which if you have a molecule, there will always be electrons. As long as there are electrons, those electrons will be in orbitals, and they'll be somewhat fluid, and they'll be able to shift around and create some charges, some temporary partial charges. So there's always the possibility of London forces. So for B, beyond the London forces, I've got some areas here that are really causing a lot of shifting in charge. And so that means as long as it's not completely symmetrical, which I can clearly see it's not completely symmetrical in all directions, it's going to be capable of dipole-dipole. So I have, these areas with large electronegativity differences, and one of its partial positives is going to line up next to another molecule's partial negative. I also have this, an OH bond. If I have an NH, OH, or FH, that sets it up for hydrogen bonding. This bond itself is not a hydrogen bond, but that shifting of electrons creates a large partial positive on the hydrogen, so it can attract to one of the oxygens from a neighboring molecule. Maybe this oxygen that has the CO double bond, and this lone pair and its partial negative, that is going to be a hydrogen bond. So I want to list that as one of the attractions as well that molecules of that sort can undergo. So what I'm doing here is I'm imagining if I had more than one of these types of molecules, what type of interactions would they have or attractions would they have? So the next one here, I realize that there is an area of partial negative and partial positive. It's not a symmetrical molecule. If I were to draw out the structure, I'll just leave out the hydrogens for now to make it a little bit simpler. The main area of a big electronegativity difference is between this carbon and the oxygen, right? This area here, where there's a big electronegativity difference. And this carbon is trigonal planar. And according to that geometry, that means that the other carbons are going to be shifted down a little bit. The angles will be about 120, but either way, the electronegativity difference is going to create some large partial charges there. So I'm always going to have one side that's permanently negative, and the other side is always going to be permanently positive. So that means it will be capable of forming dipole-dipole attraction. Can that molecule C hydrogen bond with another molecule of the same type? No, it cannot. C cannot hydrogen bond with another molecule of C. because all the hydrogens are on carbons. All the hydrogens of C have very small partial positives. A hydrogen bond requires a big electronegativity difference to create a large partial positive. Hydrogen bond is an attraction between large quantities of partial charge, not small quantities of partial charge. So C would only be able to experience dipole-dipole and London forces with other molecules of C. What about D? Well, in D, it's not really shown with the correct geometry because the sulfur, being a tetrahedral electron group geometry, is going to create a bent molecular geometry. And there is a small electronegativity difference between sulfur's 2.5 and the hydrogen's 2.1. So that small electronegativity difference is going to create some opposite charges and opposite ends. And then one molecule would line up next to another molecule, so the opposite charges would attract, and that is known as dipole-dipole attraction. D can also not undergo hydrogen bonding because, again, the electronegativity difference between sulfur and hydrogen is minimal, so the quantities of partial charge are also minimal. Question about any of those? All right, so a couple other types of intermolecular attractions. One is an ion-dipole. We talked about this. If I have a full charge attracting a partial charge, like on a water, because the oxygen is more electronegative than the hydrogen, that's a pretty strong attraction. It's stronger than the ones we talked about because it's a full charge partial charge. It's going to be stronger than a hydrogen bond, which only involves two large partial charges. With a greater quantity of positive, it's going to be even stronger. So this should probably say weaker and stronger, not necessarily weak and strong. Most ion-dipole attractions are pretty strong because it's a full charge involved in half of that attraction. But the more charge I have, the more it's going to attract to the partial negative of that side of the water molecule next to the positive too. So that makes an even stronger attraction. So again, the more charge there is, the stronger the attraction. So if I have an attraction between an ion, which is a full charge, and a dipole, which is a polar molecule that has opposite charges on opposite ends, that's an ion-dipole attraction.